After studying this module, you shall be able to know about the significance of nuclear magnetic resonance spectroscopy, the principle behind the NMR spectroscopy, and the various scientific phenomena related with NMR spectroscopy. Nuclear magnetic resonance is that branch of spectroscopy which deals with the phenomena found in associations with large number of nuclei of atoms that possess both magnetic moments and angular momentum, and is subjected to external magnetic field. That is, NMR deals with interaction of magnetic nuclei with external magnetic field. NMR lies in radio frequency region of electromagnetic radiation and is very useful for the structure elucidation of a molecule. In NMR, when nuclear under consideration is proton, then it is called proton magnetic resonance, that is PMR spectroscopy. Resonance implies that we are in tune with a natural frequency of the nuclear magnetic system in the magnetic field. A rotating object possesses a quantity called angular momentum given by the right-hand thumb rule. Spin is a type of angular momentum that does not vanish even at absolute zero. So, a physical motion to represent this type of angular momentum is not without error. Spin is a fundamental property of an electron and nucleus, like its mass, electrical charge, and magnetism. Now, we shall have a look at the principle. Nucleus contains protons and neutrons. A proton carries a positive charge while a neutron is uncharged entity. Both these particles spin around their axis with spin quantum number half. Rotation of anything is associated with angular momentum abbreviated as capital L, that is L is equals to under root I into I plus 1 into h by 2 pi, where I is the spin quantum number. According to quantum mechanics, L cannot have any arbitrary value but can point only along certain directions, which is called as the space quantization of angular momentum. These directions are such that the component of L vector along certain reference axis, say z axis, has only quantized values. This reference axis is usually considered as direction of external magnetic field, that is, Mi is given by h by 2 pi, where Mi can take the following values. For integral spin, Mi is given from I into I minus 1, I minus 2 up till minus I minus 1 to minus I. For half integral spin, Mi can have the values ranging from I minus 1, I minus 2, plus half, minus half up till minus I minus 1 and minus I. Now we shall discuss about the nuclear spin state. In NMR, certain atomic nuclei must be magnetically active for this technique to be used. However, only a certain number of isotopes have this magnetic characteristic called spin. An example is hydrogen. When an external magnetic field is applied, hydrogen spinning proton generates a magnetic moment which can either take alpha or beta spin state. The energy difference between these two states is directly proportional to the amount of external magnetic field applied. The alpha state is aligned with the applied field and has lower energy than the beta state. When a pulse of electromagnetic radiation is applied to the alpha state, it can be excited to the beta state, thus a resonance will be obtained. The NMR is only able to detect certain atoms and only certain isotopes. For example, it can detect the hydrogen molecules with a mass of 1 AMU but not the other isotopes. Most commonly, the hydrogen and carbon NMRs are used. Now, we shall study about the phenomena of NMR. A spinning charge generates a magnetic field as shown on the right. The resulting spin magnet has a magnetic moment mu proportional to the spin. In the presence of an external magnetic field B0, two spin states, that is plus half, which is alpha, and minus half, which is beta. The magnetic moment of the lower energy plus half state is aligned with the external field, but that of the higher energy minus 1 by 2 state is opposed to the external field. Note that the arrow representing the external field points north. The difference in energy between the two spin states is dependent on the external magnetic field strength and is always very small. The two spin states have the same energy when the external field is 0 but diverges as the field increases. At a field equal to Bx, a formula for the energy difference is given. Remember, I equals to 1 by 2 and mu is the magnetic moment of the nucleus in the field. Now we shall study about the origin of NMR signal. First we shall see the Zeeman effect. It was discovered in 1890s when inserted in a magnetic field B0, nuclei that possess spin align themselves according to their energy states. The Zeeman effect energy levels are: if I equals to half, then delta E given by h nu B0 is minus 1 by 2 minus plus 1 by 2. The spin states are said to be split into two populations, 1 by 2 which is anti-parallel and plus 1 by 2 which is parallel by B0. Imagine a charge travelling circularly about an axis. This is similar to a current that flows through a conducting loop. Such a circular current builds up a magnetic moment mu whose direction is perpendicular to the plane of the conducting loop. The faster the charge travels, the stronger is the induced magnetic field. In other words, a magnetic dipole has been created. Such dipoles, when placed into a magnetic field, are expected to align with the direction of the magnetic field. Note that the course of the momentum is tangential to the course along which the particle moves. The torque is formed by the vector product between the radius and the momentum and is described by the vector which is perpendicular to both radius and momentum. In fact, it is the axis of rotation which is perpendicular to the plane. The corresponding potential energy is in contrast to the behavior of the compass needle. The nuclear spin does not exactly align with the axis of the external field. It rotates, that is spins, about its own axis as shown by the blue arrow and precesses about this axis of the magnetic field B. This is called the Larmor precession. Its direction of revolution cannot be determined because once it starts revolving, it remains continuous. The frequency of this precession is same as the energy separation of two levels of alpha and beta protons and is proportional to the strength of the magnetic field. That is, omega is given by gamma into B. The proportionality constant is called the gyromagnetic ratio. The frequency omega is expressed in terms of angular velocity. It is specific for the kind of nucleus and therefore has a different value for proton, C13 and F19 nuclei, etc. The precession frequency given by omega naught is equal to nu naught into 2 pi is called the Larmor frequency. On increasing the value of B, precessing frequency starts increasing. The precession of magnetic moment means that nuclear magnetic field is rotating around the external magnetic field. Potential energy of nucleus remains constant in this precession. Potential energy can be changed by changing the orientation angle of magnetic moment vector to other permitted angle. This can be achieved by applying secondary magnetic field rotating around the main magnetic field with a frequency equal to that of the precessing nucleus. Under these conditions, the rotating magnetic field is in resonance with the precessing nucleus from one level to another, giving rise to either absorption or emission spectra. The frequency difference between the two levels is given by delta mu equals to 42.6 MHz times B. Thus, a proton in the lower energy level, that is Mi equals to 1 by 2, can be promoted to the higher energy level, that is Mi equals to minus 1 by 2, in the presence of a magnetic field by supplying the necessary energy in the form of electromagnetic radiation of frequency equals to 42.6 MHz. Such type of transition is the subject of NMR spectroscopy. Now, we shall see the experimental setup of NMR spectrometer. To begin with, the NMR spectrometer must be tuned to a specific nucleus, as this case the proton. The actual procedure for obtaining the spectrum varies, but the simplest is referred to as the continuous wave that is the CW method. A solution of the sample in a uniform 5 mm glass tube is focused in between the poles of a powerful magnet and is gyrated to average any magnetic field variations as well as the tube imperfections. Radio frequency, that is the RF radiation of suitable energy, is transmitted into the sample from an antenna coil shown as red colored. The sample tube is surrounded by a receiver coil and the emission of energy absorbed is observed by the electronic devices and a computer. An electric current passing through such a coil generates magnetic field in its center and directed along the axis. This magnetic field reverses its direction with same frequency as current from the oscillator. This alternating magnetic field is equivalent to the rotating magnetic field, which is rotating in the opposite directions with the same frequency. One of these directions is same as that of the precession motion of the nucleus, and thus field rotating is in the direction acts as a secondary magnetic field. When the frequency of alternating currents applied to coil and the magnetic field experienced by the nucleus have values equal to the frequency of separation between the two energy levels, a condition of resonance exists, and thereby the nucleus can either absorb or emit energy from secondary magnetic field. There will be net absorption of energy as the ground state level is more polluted than the excited level. This is called the spin resonance spectroscopy. The above resonance phenomena can be achieved by either of the following ways. An NMR spectrum is acquired by varying or sweeping the magnetic field over a small range and keeping the frequency of RF radiation constant. A similar effective method is to differ the frequency of the RF radiation while holding the external field continuous. In the first case, lambda frequency is kept constant and the external magnetic circulating magnetic field varies till it becomes equal to the lambda precessional frequency. However, in the second case, frequency of the external circulating magnetic field is kept constant and the lambda frequency varies till it becomes equal to the frequency of the external circulating magnetic field. In actual practice, it is preferred for most instruments to use a fixed frequency, usually 60 MHz, supplied from a radio frequency oscillator and to fluctuate the magnetic field applied to the sample by an electromagnet. Because variation of magnetic field can be achieved easily as compared to the variation of the frequency. Now we shall see the applications of NMR to molecules. It is expected that all the hydrogen atoms might give resonance signals at the same frequency values as all protons have identical magnetic moment. Providentially, for chemistry applications, this is not true. It is not possible, of course, to study isolated protons in the spectrometer discussed above. But from independent measurement and calculations, it has been determined that a naked proton would resonate at a lower field strength than nuclei of covalently bonded hydrogens. With the arrival of Fourier transfer instruments in the 1970s, it has become possible to acquire spectra of nuclei that are not naturally abundant, such as C13, which is only 1.1% naturally occurring. This requires the acquisition of multiple spectra and adding them together to get a greater sensitivity. The signal to noise ratio, that is S/N, will increase as acquisitions increase because the signal magnitude increases linearly with acquisition number while the noise magnitude increases as the square of the acquisition number. So, the S/N ratio will increase as the square of the number of acquisitions increases. Currently, NMR spectrometers use the Fourier transform method of pulse radiation. To change the nuclei in the alpha state to beta, a strong pulse of radiation is used. Then, the pulse of radiation is removed and the nuclei go back to their original alpha state, giving a decay signal. This signal is converted by the computer to a frequency domain spectrum in a very fast method. By storing many signals, a more intense spectrum is produced. Now we shall learn about the phenomena of chemical shift. The location of different NMR resonance signals is dependent on both the external magnetic field strength and the RF frequency. Since the resonant frequencies will vary continuously, no two magnets will have accurately same field, due to which another method for characterization and specification of location of NMR signals is needed. One way of resolving this issue is to report the location of NMR signal in a spectrum comparative to a reference signal from a standard compound added to the sample. Chemically unreactive and easily removable sample should be used as a reference standard, which should be able to give a single sharp NMR signal that does not interfere with the resonances which is normally seen for organic compound. Tetramethylsilane, that is CH3,4Si, usually mentioned to as TMS, standing for tetramethylsilane, fulfills all these features and has become the reference compound of choice for many proton and carbon NMR. In order to provide an explicit location unit, an additional step is required as separation or dispersion of NMR signals is dependent on the magnetic field. To correct these frequency dissimilarities for their field dependence, we divide them by the spectrometer frequency. The resulting number would be very small since we are dividing Hertz by megahertz. So, it is multiplied by 1,000,000 as shown by the formula given below. We should note that mu reference is the resonant frequency of the reference signal and nu sample is the frequency of the sample signal. This operation gives a number called the chemical shift, having units of parts per million, that is ppm, and designated by symbol delta. That is, delta is given by mu reference minus mu sample divided by mu reference into 10 to the power 6. Electrons around a magnetic nucleus produce a local magnetic field opposite to the applied magnetic field. Magnetic nuclei can absorb the electromagnetic pulses at specific frequencies named chemical shifts or the signal positions expressed in parts per million, that is the ppm. These chemical shifts are designated relative to a standard compound such as a derivative of tetramethylsilane, that is TMS, which is CH3,4Si, which has a chemical shift of 0.0 that is soluble in water. The field strength and resonance frequency are directly proportional. Doubling or tripling the field strength will double or triple the distance in Hertz of the observed peaks relative to tetramethylsilane. To make it easier to compare reported literature data, we standardize the measured frequency by dividing the distance to tetramethylsilane in Hertz by the frequency of the spectrometer. This procedure yields a field-independent number called chemical shift delta. From the preceding discussion, it may be assumed that one factor responsible for chemical shift dissimilarities in proton resonance is the inductive effect. The induced field due to electron motions will be stronger in the case of high electron density around a proton nucleus as compared to field induced due to low electron density. Thus, the shielding effect would be larger in such high electron density cases, and a greater external field B0 will be required for the RF energy to excite the nuclear spin. When the electromagnetic pulse runs through the sample, alpha spin nuclei that are hit with the correct amount of energy switch to beta spin and subsequently cause resonance. This resonance can be then recorded and is reported for different frequencies applied to the sample in ppm chemical shifts. Since silicon is less electronegative than carbon, the electron density above the methyl hydrogens in tetramethylsilane is expected to be greater than the electron density above the methyl hydrogens in other organic compounds, and the characteristic resonance signal from silent derivatives does indeed lie at a higher magnetic field. Such nuclei are said to be shielded. Opposite effect, that is the reduction in the density of electron, is shown when the elements are more electronegative than carbon, but the data presents that lower field signals, that is the de-shielded, are displayed by such elements when bonded by methyl groups. The electronegativity of the electron withdrawing groups is roughly proportional to their de-shielding effect. Moreover, in case of presence of more than one such group, de-shielding is additive and proton resonance is moved even further downfield. Now we shall talk about signal strength. The vertical axis of the spectrum displays the intensity or the magnitude of NMR resonance signals and is proportional to the molar concentration of the sample. Thus, a small or dilute sample will give a weak signal, and doubling or tripling the sample concentration increases the signal strength proportionately. This is an important relationship when samples incorporating two or more different sets of hydrogen atoms are examined, since it allows the ratio of hydrogen atoms in each distinct set to be determined. To this end, it is necessary to measure the relative strength as well as the chemical shift of the resonance signals that comprise an NMR spectrum. When evaluated relative signal strengths, it is useful to set the smallest integration to unity and convert the other values proportionally. Now, looking at the integration. Integration is very useful in NMR spectrum in determining the structure of a molecule. The relative integrated intensity of a signal is proportional to the relative number of nuclei giving rise to that absorption. Normally, an NMR spectrum will give complex integration numbers. However, integration doesn't have to be exact. One can just divide each integration number by the smallest number in the NMR spectrum. The ratio would help to get a big picture of the relative number of hydrogens represented by a peak. Combining the chemical shifts and the peak integration, the structure of a molecule may be determined using the chemical shift table. Now, looking at what is coupling. J coupling arises from the interaction of different spin states through the chemical bonds of a molecule and results in splitting of NMR signals. This coupling provides detailed information about the connectivity of atoms and the structure of a molecule. Spin-spin splitting is given by the following n+1 rule. That is, number 1, by one hydrogen resonates as a doublet. Number 2, hydrogen that is neighbored by two sets of equivalent hydrogens resonates as a triplet. Number 3, hydrogen that is neighbored by three equivalents of hydrogen resonates as a quartet. A multiplet can be shown when there is a mixture of coupled patterns, some of which could be broken down to small parts, that is, quartet of doublet. But for the most part, if a coupling pattern shows complexity not easily countable by n+1 rule, such pattern is then called a multiplet. In addition, functional groups containing alcohol, such as alcohol carboxylic acid, have a broad band on the NMR spectra. This is due to the fact that hydrogens on alcohol can hydrogen bond easily, thus being able to couple in broad spectra than other hydrogens. Thus, just by looking at the type of spectra such as multiple peaks or broad peaks, one can easily categorize the functional group to which the hydrogen is associated with. The ratio of the splitting peaks is given by a mathematical mnemonic device called Pascal's triangle. Each number in this triangle is a sum of the two numbers closest to it in the line above. It is important to remember that non-equivalent nuclei mutually split one another. In other words, the observation of one split absorption necessitates the presence of another split signal in the spectrum. Moreover, the coupling constants for this pattern must be the same. Double and triple bond characteristic chemical environments show complex splitting peaks. An alkyne, for example, can have hydrogen splitting patterns and extra adjacent carbon away. An alkene, depending on whether the hydrogen is located cis or trans to a relative chemical environment, can show a slightly distorted peak. Figure 5 shows the Pascal's triangle is symmetric. This shows that the formula for the binomial coefficient, as shown by equation 1 Cmn, is given by n factorial into m factorial divided by n minus m factorial, where n is the number of hydrogens in the nearest neighborhood, and then it will be replaced by n plus 1 peaks in high resolution spectra, and relative area of these n plus 1 peak will be given by the above formula 1, and m is the number of signals that can vary from 0 to n minus 1 values. Now we shall see the Proton NMR interpretation. To interpret Proton NMR, it is important to know where each type of proton lies. It is important to know that Proton NMR peaks only indicate the presence of proton. It does not show other atoms like carbon, oxygen, etc. As mentioned in the above section, proton peaks show splitting because of coupling by the neighbor protons. The integration of each peak is the amount of proton relative to other proton in the NMR. While solving structure for the Proton NMR, it is important to write down the chemical shift, integration and the split of each peak. Then, based on the chemical shift of the peak, write down the possible functional groups and the structure. Lastly, arrange and connect these structures so that it matches the split and the integration of Proton NMR. Table 1 shows the different type of protons and the chemical shifts. The information that can be determined by the NMR is immense. In case of hydrogen NMR, one can use a certain amount of knowledge from a table to determine what each peak corresponds to which group within the sample. Interpreting NMRs can also be a little tricky in that one must understand the splitting patterns. For example, the carbon atom you may be examining may have only one hydrogen attached. However, if attached to a methyl group, it will appear as a quartet. Protons in different chemical environments are shielded by different amounts. When a nucleus surrounded by electrons is exposed to a magnetic field of strength H0, these electrons move in such a way so as to generate a small local magnetic field H local opposing to H0. As a consequence, the total field strength near the hydrogen nucleus is reduced, and the nucleus is thus said to be shielded from the magnetic field strength by its electron cloud. The degree of shielding depends on the amount of electron density surrounding the nucleus. Adding electrons increases shielding, their removal consequently would cause deshielding. Also, a proton is deshielded when the induced field reinforces the applied field. For example, the induced field can reinforce the applied field. As a result, these protons are deshielded and their chemical shifts are at a higher value of ppm. Now, we shall summarize what we have learned in this module. Nuclear magnetic resonance is that branch of spectroscopy which deals with the phenomena found in association with large number of nuclei of atoms that possess both magnetic moments and angular momentum, is subjected to external magnetic field. In NMR, when nuclei under consideration is proton, then it is called proton magnetic resonance, that is the PMR spectroscopy. In NMR, certain atomic nuclei must be magnetically active for this technique to be used. However, only a certain number of isotopes have this magnetic characteristic called spin. An example is hydrogen. The NMR is only able to detect certain atoms and only certain isotopes. For example, it can detect the hydrogen molecules with a mass of 1 AMU but not the other isotopes. Most commonly, the hydrogen and carbon NMRs are used.